Welcome to the lesson for Wednesday, 127. We're taking a look at adding and subtracting radicals and roots now. So we'll just talk about the property of adding and subtracting. The property says that if I have the nth root of a plus the nth root of a, that would make 2 nth roots of a. Notice I'm not adding what's inside. I have one of them, I have two of them, 2 total. And in more general terms, if I have b nth roots of a plus c nth roots of a, that would make a total of b plus c nth roots of a. Now that just seems a little off the cuff. So what does that really look like? And I think the properties maybe make it more confusing than it really is. So let's just take a look at an example. What these properties say is that if the index and the radicand are exactly the same, so both n and a are exactly the same, then you just count how many you have. I have 1 here and 7 here. So I have a total of 8 fourth roots of 10. And that's what's happening right here. 1 plus 7. You're just adding the coefficients. So here, these are not radicals, these are in rational exponent form, but these are still radicals, that just means the 5th root. But I have the exact same thing. I have the same index 5, and I have the same radicand 8. So how many total of these 8 to the 1/5 power are there? I have 2 plus 10, or a total of 12 of these 5th roots of 8. So again, as long as these are exactly the same, all you have to do is add and subtract the coefficients. That's it. It's the same thing as saying 2x plus 10x equals 12x. Instead of x, though, we have 8 to the 1/5 power, or whatever it might be. Then I get to this guy, and I see they are not the same. The radicands are different. Do not call this the cubed root of 52. You can't do that. You have to have the same radicand. So what we're going to do is we're going to break this one down. I know that 27 is a perfect cube root. 27 times 2 is how I'm going to break up 54. And then I take the cubed root of 27, which is 3. It's perfect, so it comes out. So I have 3 cubed root of 2 minus 1 cubed root of 2. 3 minus 1 is 2 cubed root of 2. So I break it down so they do have the same radicands, and then I can add and subtract. But you have to break it down first. We can do this with variables as well. As you can see here, these are exactly the same. 5 of these plus 6 of these makes 11 of those square roots of 1. And I don't touch the square root of 1. I'm just counting how many I have, 5 plus 6. Now over here, these are not the same radicands. So again, I need to break these down. So I'm going to break down not 2, but z to the 5th is z to the 3rd and z to the 2nd. 3 divided by 3, that's perfect. Here I have a z. I'm going to break up 54. I need a perfect cube. That's 27 times 2, z squared. So let's break up this one. The only thing perfect in here is z to the 3rd. So 1z comes out, and the cube root of 2z squared is left. Here I have 1z outside. What's the cube root of 27? So I have 3z cube roots of 2z squared. So do I have like terms? Yes, I do. Z cubed root of 2z squared. These are exactly the same. How many do I have? I have 12 of them minus 3 of them, or a total of 9 of these z cubed roots of 2z squared. If you have questions, pop back in the live session. Otherwise, get started on your homework.